Hello. Um, what we just talked about in our latest lesson was velocity in rotating frame, and now we're going to talk about acceleration in rotating frame. So we have a frame, an arbitrary frame. It rotates about our inertial frame, and we characterize the rotation with this angular rate matrix. All right. So we know that to derive an equation for acceleration, we need to differentiate velocity. All right. So just one thing here, note that because we're going to use this later, we derived this equation when we were talking about velocity in rotating frame. This R circle was relative velocity with respect to rotating frame, and R dot was our time rate of change in our inertial frame, our actual velocity or inertial velocity. Now, note that in deriving this equation, we did not make any assumption about what R is. Right? R could be position vector, it could be any other vector. So this is also true if we were differentiating an arbitrary vector in our rotating frame. So for example, let's say we have a vector which is called A. For that vector, you could do the same thing. You could say A dot is a circle plus omega cross A. Right? So, and then we're going to use this this mathematical relationship when we are deriving acceleration for it. The first step to derive the equation for acceleration is simply to differentiate our velocity relationship. So what we're going to do is we're going to say, all right, on the left hand side I have R dot, right? And I could say, just to make it easier for you to understand, I could say R dot double dot is, in fact, we know that it is R dot, which is dotted again, right? We have already differentiated once and we differentiated again. Now, go back to what I have here. What they said here was, this is a relationship for any vector, right? Now, let's say I'm replacing my A with R dot, all right? So this is a general relationship we had. We just derived it in our latest lesson. And I'm going to replace this A itself with R dot. What do I get? I get, on the right hand side, I'm replacing A with R dot. So I get R dot, and it is circled. And I'm replacing this A with R dot 2 plus omega cross R dot. All right. Now, what do I do next? Right. So again, we are going back and use the relationship we have already derived in our latest lesson. So this time I'm going to use this relationship. So R dot is R circle plus omega cross R. So what I get here is left hand side is equal to, I'm going to replace this R dot with R circle plus omega cross R. So the circle is still outside. So I have circle plus omega cross R, right? This whole thing is going to be circled, right? The circle now applies to both terms. So again, circle was when we differentiated our vector in our rotating frame. All right. And then we have omega cross R dot. So I have omega cross, again, I'm going to replace R dot with R circle plus omega cross R. To remind you what we are doing here, again, so if you recall for velocity, I explained that our goal is to have all the dots on one side, left hand side, and all the circles on the right hand side. In other words, this is what I'm doing here. I'm trying to move all the circles to the right hand side and I'll just have dots on the left hand side. Okay. And this way, at the end, we can relate different time rate of change in inertial frame to time rate of change in a rotating frame, plus some terms depending on angular velocity vector. So, alright, this circle applies to both terms. If you don't understand it as a circle, then you can think about it as d dt. Alright, so when you apply d dt to both terms, what happens? So you apply them to each of the terms and add them together. Alright, so this is what I'm going to do. I'm going to apply the circle to both terms. Right. So circle, circle. Alright, it is as if you have a double d dt and you differentiate two times. Plus, now here, I'm going to simply use the product rule. So I'm going to apply this circle, which is again a d dt, to both terms. So I have plus, so differentiated first term, cross product the second term, differentiated the second term, cross product the first term, and add them all together. All right, what do we have here? We can simply expand this bracket and get plus omega cross r. All right, we are good now, because now you can already see that we have achieved our goal. On the right hand side, we only have circles. We have, you can call this a relative acceleration. Then we have differentiated our angular velocity matrix. All right, and then we are differentiating r in our relative in our rotating frame. So that's the circle indicates. Differentiating our parameter in our rotating frame is denoted by or using circle. So what I have here is, and then I'm going to group terms. So I have two of these. So r circle, circle. This is a circle. Plus 2 times omega cross r circle. Plus omega circle cross r. Plus omega cross r. Now, in dynamics, each of these terms have a name. So left-hand side is obvious. It is absolute acceleration with respect to our inertial frame. This term here is, let me use a different color. So this is relative acceleration as seen in the rotating frame. To omega cross r circle is called Coriolis acceleration. Probably many of you are already familiar with that. So 2 omega cross r circle is Coriolis acceleration. All right, so when you look at Coriolis acceleration, note that whether omega varies or changes, or r, the relative velocity, so we named our circle our relative velocity, or relative velocity changes, our Coriolis acceleration changes. And you also note that this is a cross product. Right? It is not only depends on the magnitude of omega and r circle, it also depends on the direction of omega and r circle. And then we have omega circle cross r. This term is tangential acceleration. Okay, think about it for a moment, why it's called tangential acceleration. And omega cross r is centripetal acceleration. So centripetal acceleration. All right, let's see. Just one thing here. So on the right hand side, one term which could be a little bit confusing is omega circle. What does it mean to differentiate omega in our rotating frame, right? So let's see what happens. So what does it mean? Again, what I'm going to do here is that I'm going to use this expression we had. So we talked about this relationship. We said that this relationship, A dot is circle plus omega cross A, applies to any vector in a rotating frame. In other words, if you wanted to differentiate any vector in rotating frame, you can use this relationship. So what I'm going to do is now I'm going to replace my A with omega itself and see what I get. So here I have omega. That's what I'm interested in, omega circle, right? So let's use this relationship, replace A with omega. So we have omega dot equals omega circle plus omega cross omega omega. All right, so now you could easily see that. What is omega cross omega? This is a cross product of a vector by itself. The sine angle, the angle between the two is 0 now. So sine is 0 is 0. So this term goes to 0. So from this, we conclude that omega dot is omega circle. So essentially we have shown that here, for tangential acceleration, you can replace omega circle with omega dot. And that this should quite make sense now, because omega was angular velocity. We differentiate it with respect to time and simply get angular acceleration, and that's it. So these are the terms we have in rotating frame. And now, next step, next lesson, we're going to use this information, this small piece of information, and along with the latest lesson, to talk about velocity and acceleration of an arbitrary point in rigid body. This is where we started. We started with a rigid body. We said that our goal is to derive velocity and acceleration of the rigid body in a frame attached to the rigid body and relate that to absolute velocity and accelerations. So now we have done this. We're going to talk about, all right, so what if our frame, our rotating frame, is attached to a rigid body? What would it be? So how does it affect these equations? Does it make it easier? Does it make it simpler? Or is it making does it make it more difficult and more complicated? All right. So see you later.